Okay, we are now on example number 7 and about to end the topic of the improper integral. Again, in this example, you are given an integral that may look like an ordinary definite integral, having limits which are real numbers. So you have the integral of 1 over the square root of x minus 2 to be evaluated from 2 to 5. Now, if you look very closely on the limits and also on the function that appears on the integral, if you will have a division by 0 here, meaning the answer of this radical expression would be a 0, your answer will be non-existing because your answer will be infinity. And then you try to ask yourself, what number will I place for the x in here that would either fall in between these two numbers or on any of these two numbers that will make the square root of this particular expression 0. Okay? So some of you would say, or probably all of you would say, if you place a value of 2 for the x, I will have a division by 0. So first we note that the given integral will be improper because the given function has a vertical asymptote at x equal to 2. We know that for the type 2 improper integral, we will have what we call as the vertical asymptotes. That's the line x equal to something where your curve of the function will be asymptotic to, or one part of the curve of your function would be asymptotic to. And if it is said to be asymptotic to that particular line, which is x equal to something, you have what we call a vertical asymptote. Now, you have an infinite distant continuity here occurring at the left end point at 2, 5. So this is case 2b, wherein you have in here one of the limits of your integral producing a function which will be infinite. So you have here, now to evaluate the integral, this is your original integral, you have to evaluate it in using the concept of the limit. So you change this particular value of 2 in which your particular function would be asymptotic to, and then you place t for that. And then t will be approaching 2 from the right. So it's 2 plus, so we know that it will be approaching 2 from the right side of the integral. So you have the integral of 1 over square root of x minus 2 to be, so we know that this is x minus 2 raised to negative 1/2. So if you're going to evaluate this, you're using the power rule, you will have x minus 2 raised to 1/2 all over 1/2, which will yield to square root of x minus 2, right? Knowing the rules of exponents, you make the exponent of this expression raised to negative 1/2. So the answer of this integral actually is this. And you will have the limit t to 5. And now you could see that you have now eliminated the symbol of the integral and you placed here the limit of t approaching 2 from the right, because this is the value in which you're going to substitute your x here, which will make your original given integral asymptotic to itself, to the line x equal to 2. So now when you substitute the limit, so the first part is you substitute, of course, the upper limit, which is 5. That would be 5 minus 2, and that would be square root of 3. If you substitute for the x the t, that would be then t for the x minus 2. And if you substitute now, or rather you're done with the substitution, if you will now evaluate this one, if you substitute t equal to 2 to this will be the square root of 0. Thus, the value of this limit actually equivalent to this original integral will be 2 square root of 3. Thus, the given improper integral is convergent as we have learned in the past, since the value of it is a real number. If there is no value associated to it, then the said integral will be what we call a divergent integral. So this is how we evaluate this integral, which has a point, or rather an asymptotic point in the curve, which is x equal to 2. So it's asymptotic on the line x equal to 2, approaching it from the right side. Okay? Now we will continue. So this is how it's going to look like. It's like you have here the x equal to 2 line, and this is the curve of your function, and that area in which we will determine the value of is the 2 square root of 3. And remember, the 2 square root of 3 is the value of this particular integral. And that is the same area under the curve on the limit 2 to 5. So actually, these are the limits of your integral. So it sets the boundary. So the limits of your integral sets the boundary for the area under the curve. So the area here is equal to 2 square root of 3. So this is the area that we're trying to find. So this is the value of such area. But notice that you have here this particular part of the curve being approached from the right side, which is asymptotic to this line x equal to 2. Okay? Now we proceed. So a comparison test for improper integral. So sometimes it's impossible to find the exact value of an improper integral. And yet it is important to know whether it is convergent or divergent, meaning there are problems that will not ask you to evaluate the value of a given improper integral, but will simply ask you whether it's convergent or divergent. In such cases, the following theorem is useful. So although we state it for type 1 integrals, so a similar theorem is true for type 2 integrals. So actually, it's the same as that. So similarity applies to both. Now, suppose, so this is the comparison theory. That means you will only apply this if you're given an improper integral which will not require you for each value. It will not ask you what is the value, but rather it would simply ask you to tell whether it's convergent or divergent. So this is where you're going to apply this comparison theorem. So let's say, for example, you're given two functions, and the function of x is said to be the function of f of x is greater than g of x, where g of x is greater than 0. Now, this particular condition holds true if your x is greater or equal to a. Now, if this is the case, if this is the condition, and our two continuous functions, meaning it does not have any point of discontinuity, it's continuous for the value of x equal or greater than a, then this too applies. If the integral of the function of x from a to infinity is convergent, it follows that the integral of g of x from a to infinity will be also convergent. Why? Because the function of x is greater than g of x, meaning g of x, this g of x is just under your function of x. In terms of the graph of the function, the g of x is under the function of x graph. If that is the, no, yes, it's under the function of x graph. So if that is the case, your function of x, which is convergent, tells you that your g of x will also be convergent because its value is, as I've said, lesser than the function of x. If g of x is divergent, what about if g of x is divergent? Then the function of x is also divergent. Now, this would be quite difficult to absorb if it's just in sentence form, but you have to understand this. This is the condition in which this two applies, okay? The function of x is greater than g of x, which is greater than 0 for all x values equal or greater than a. This will be properly understood if we will have an illustration. This is your function of x, which is said to be bigger than the function of g of x. The area of g of x is the pink or the peach curve here. The area under the function f of x is the blue one, including, of course, the area under the g of x. So if we go back to the first one, actually, it's so easy to understand. It follows that if your function of x, which is greater than g of x, is convergent, so meaning this one, this function here with the blue area is convergent, it follows the one under it would also be convergent because this one is higher than g of x. The other letter that we're going to apply in the same illustration is this. The g of x, which is under f of x because the value is lesser, is divergent. Then we can conclude that the function of x will also be divergent. So since if this is divergent, the one on top of it will also be divergent because it's under the said function. So if this is convergent, if f of x is convergent, it follows that g of x is convergent. If g of x, which is lesser than the function of x, is divergent, it follows that f of x is divergent. So we're just simply comparing one to another. So kung nakabalo na tayo, we know that this one is convergent and the other one will be convergent. If this one is divergent, this one also be divergent. Where do we apply it? On this particular condition, stating specifically that the two functions are continuous. Okay? Now, we'll have another one. So, we'll have another, shall I say, a corollary to that particular comparison theorem. Okay? This is it. Note that the reverse is not necessarily true. Meaning, what if we reverse the two statements that we have there in the comparison theorem? It is not true. Meaning, kung sulion mo, correct man siya gali. How does it apply in form of a statement? So this is the shall I say, the opposite of the original comparison theorem. So you have here the g of x is convergent. So remember, the g of x is lesser than the f of x. F of x may or may not be convergent. So if this time, kaina sa first tuya ang imo nga function of x ang convergent. So ang imo nga g of x, it follows that it is convergent. Pero if we change the statement, if we say if g of x is convergent, it may, referring to the function of x, it may or may not be convergent. So it could be that pwede siya mag-convergent kay g of x, pero ang function of x doesn't follow to be convergent. It could be convergent, it could be divergent. Now, in terms of the second statement, in the second statement, we say that if g of x is divergent, the function of x is also divergent. Now, in here, if we reverse the statement, if the function of x is divergent, g of x may or may not be divergent. So, hindi siya nag-follow through nga kung divergent. Si function of x, si g of x mo, may or may not be divergent. So, this is the comparison theory. You can use this in determining whether the function will be convergent or divergent without having to find its value. Now, how do we apply that to a particular situation? So I think this is the last example in this set of slides. So show that, that the integral of e raised to negative x squared from 0 to infinity is convergent. It does not ask you to determine the value, but it's simply asking you to determine whether this particular integral is convergent. Now, this comparison theorem class is actually applicable for what we call non-elementary definite integral. So this one is a definite integral, specifically a definite improper integral, but this is non-elementary. Why do we say non-elementary? Because if you look at the function, you cannot have this integrated simply. It's non-elementary. So in terms of complexity, it's really complex. So you cannot determine its value unless you change this infinity here, or you substitute limits to the integrals, which will allow you to process this in your calculator. Without your calculator, you cannot process the value of this particular definite improper integral because it is said to be non-elementary. So there's no need for us to determine the value. We just simply need to know whether the function is convergent. So it says here we can't evaluate it. And the antiderivative of e raised to negative x squared is not an elementary function. So I've stated already. So what do we do now? So we can write the integral of e raised to negative x squared from 0 to infinity in this manner. So we split it. So we can have 0 to 1, same function, added to the integral using the limits 1 to infinity. So the upper limit of the first is the lower limit of the second, having these two, the sum of these two integrals, the same as the original. So we observe in here that the first integral on the right-hand side is just an ordinary definite integral. Why would you say that this one is an ordinary definite integral? Because if you use your calculators now, if you have it with you, this will give you right away an answer. This is an ordinary definite integral. Your problem would be the second one, because their calculator cannot process this for you. So we need to replace this one with something, a plausible replacement. When we speak of plausible, class, ng acceptable replacement to this particular integral, which will allow us to determine whether uh, the original integral here, without knowing its value, is convergent. This one is convergent. We know it has a value. But we cannot conclude right away that if this one particular integral is convergent, the other one is convergent already. Therefore, the original integral is convergent. There is a need for you to know whether the second term here is also convergent. And what would that assumption be? Okay, or what would that plausible replacement should be? Now, in the second integral, we use the fact that for x greater than 1, the value of x squared will always be greater than x. We know that 1 or 2 squared is greater than 2. 3 squared is greater than 3. We know that. And so, we know also that the greater is the negative value of anything that makes the value of that thing less. Like we say, negative 1,000 is less than negative 50 in value, right? So the greater the numerical value of a negative number, the lesser is its value. So this is why it's written like this. The negative of x squared is less than the negative of x. Shall we say negative 9 is less than negative 3? Or negative 100 is less than negative 10. So if this applies, this one is where it's coming from, for all x values greater or equal to 1, and this applies, therefore we say that e raised to negative x squared would be less than or equal to e raised to negative x. Actually, even if this is not stated here in the form of a conclusion, you can check in your calculator. If you have e raised to negative, let's say 100, the value of that would be lesser than e raised to negative 10. You can check that because the greater the value of the negative exponent of the exponential function, the lesser is the value of the entire thing. So if you're going to graph the two functions, so the upper curve here, the upper curve, the purple or is the pink curve, the fuchsia pink curve is your e raised to negative x. It's greater than the blue curve, which is e raised to negative x squared. Now, since we want to use the comparison theorem, and we know that this e raised to negative x, the purple curve is, or the fuchsia pink curve is greater than e raised to negative x squared, we may use this one. The integral of e raised to negative x is easy to evaluate. So we can use its integral when we speak of in u, in place of e raised to negative x squared. So, islan ko na di si negative x squared sang negative x lang. Then I will evaluate the limit again of the integral where the infinity here will be replaced by t, and that's the value in which your limit variable is going to approach to. So you have this. If you integrate this, your answer will be negative e raised to negative x, right? EU du is EU. However, the du of this is negative. So that's why you see here a positive answer. Negative dx, so you place negative here, and the answer of this is EU du. So it would be e raised to negative 1 minus e raised to negative t. Now, you see that there is a, shall I say, an interchange, because this one should be the upper limit and this one should be the lower limit. But since we have the negative for the derivative of the negative x here for the negative dx, so the two was interchanged. Okay? So your EU, which is e raised to negative x, is actually negative e raised to negative x. However, we interchange the manner of substituting the limits. So now we have it as e raised to negative x only, provided that we will have the lower limit substituted first, followed by the upper limit. Now, if you substitute the lower limit 1, so it will have, of course, a specific value. And if you substitute the upper limit, which is infinity, e raised to negative infinity is 0. So your answer here is e raised to negative infinity. So you see, the integral of e raised to minus x, which is greater than the integral of e raised to minus x squared, has a definite value. So using the comparison theorem, we can therefore conclude that our integral of e raised to negative x squared dx is convergent because the integral of e raised to minus x, which is greater than this one, is convergent. So we used letter A of the comparison theorem actually. We made use of this. So we replace the original integral by a plausible integral, acceptable integral, greater than it, and check whether the value of that greater integral function is convergent. And since it's convergent, we conclude that our integral here is convergent. We don't know the value of this, right? We did not find its value, but we concluded it's convergent because of the comparison theorem. Okay? So this ends this particular set of slides on the improper integral. I would understand if this will not come as easy as the other topics of the even the indefinite integral, because when you speak of improper integral, it's something that is not easily grasped. Hindi siya hapos i-grasp because it thinks of replacing your original integral by the integral, or rather by the limit of that particular integral, wherein we change a particular limit of that integral into t or into x and evaluate not the integral itself but the limit of the integral and find the value. So as a review, just to cap up on everything that we have discussed so far, I will not show this one. I'll go back so that everybody get to be refreshed on the improper integral. So we know that um, improper integrals can be convergent or divergent, and it can be any of these two types. The one which is easy, type 1 is easy because any of the two limits can be infinity or both limits can be infinity. Type 2 is easily misunderstood to be a common integral, but it should not be because you have to check whether on the given limit your integral will be existing or not, or in between the two limits whether it will have a point of discontinuity. So there is a type 2, pwede na nga diri siya maging infinity, pwede siya diri mag-infinity, or in between the two it would be infinity. So that's where the common mistake usually happens because it's mistaken to be an ordinary definite integral. This one has three cases. One in which the upper limit is infinity, the lower limit is negative infinity, or both is negative infinity to positive infinity. This one has also three cases just like this one. So one case wherein you have the point of discontinuity here, so meaning you have a vertical asymptote here. It could be that you have a vertical asymptote here, or it could be in between there is a point of discontinuity. So three cases also. And the terms convergent and divergent is applicable to these two types. Convergent if the limit of the integral is existing. Divergent if the limit of the integral is non-existing. Another thing that you should remember between these two types of improper integral is the graph of type 1 improper integral is could be infinitely extending either to the right or to the left, meaning our basis is the horizontal axis. In the case of type 2, the point of discontinuity or the graph of the function will be infinitely extending to on the vertical axis. That is why it has this term here, integrals with vertical asymptotes, because it would either be extending upwards or downwards in reference to a particular line x equal to something. It could be 0, -1, 1, or 2. Okay? Now, this is the topic of the improper integral. Do you have any question, anything that you'd like to ask me before I go to the concept? Actually, the numerical integration slide is very short and you will find it likable. 10 times likable than this topic, because all you have to do is substitute to a given set of formula and follow a set of procedures. Any question here? Do you understand the improper integral already? So whenever you see a definite integral, please check always whether it's type 2 or not. Type 1, you will know already right away. But type 2, that's where the common mistake is. Okay, so if there are no answers, there are no questions to this one, I'd like to share a new set of slides. And that would be the numerical integration part. Okay, so I have 23 minutes. So let's finish this in 10 minutes. Oh, just joking. Anyway, but actually this is one very easy to understand topic in integral calculus. Now, as easy as power rule. Okay, we go to numerical integration. It's an application, an elementary application of the definite integral. However, its primary purpose is in approximating only. So meaning it does not give you an accurate answer, as accurate as if you have evaluated the given integral using a calculator or a software for that matter. So these are our learning objectives. So approximate value of definite, take note, non-elementary integrals. And we have only two methods to learn here. The first one is the trapezoidal rule, and the second one is the Simpson's rule. Actually, in these two methods, you don't do any integration. However, why is it included in integral calculus? It approximates the value of a definite non-elementary integral. So what are examples of non-elementary integrals? So these are non-elementary integrals. In our language, in our vernacular language, budlay ni sila i-integrate kaya hindi gani sila elementary, kumbaga college na or masteral na or postgraduate, doctoral na sa integral nga mga expressions ang ginahatag. So one was given to you a while ago. This one, the e raised to negative x squared. So it's a non-elementary function. When you integrate such an integral, it's really very difficult unless you are that proficient and you are that good in the evaluation of such integrals. So we will learn from this for this afternoon how to determine the value of these non-elementary integrals. Okay, so we will use the process of approximation using the method of numerical integration. Why did I say we will only learn trapezoidal rule and Simpson's rule here? Because there are also other numerical integration techniques. But what is included in our undergraduate curriculum is only these two. Okay? Now, when you speak of the trapezoidal rule, if this is the area of the curve in which you are to evaluate, you will approximate its area by using a trapezoid. So what's a trapezoid? It's a plane figure in which the two sides are parallel, and you have this particular side also, and this side not being parallel already. Because if I will extend this side and with this, they will come to a point in which they will meet. So this is a trapezoid. So look at it. This is an expanded view of a particular portion of a curve wherein you use the area of a trapezoid to approximate the area of the curve. So this one was not accounted for, this area here, this one also, and this one. So what you're going to give us an answer for the area of the original curve is just the area of this trapezoid. Now, to address the problem of having it so crude, it's a very crude approximation, very crude. You cut this particular curve into smaller trapezoids. So the more cut you make, the more approximate is your, the more accurate is your approximation. Because if I make a smaller trapezoid here, another smaller trapezoid here, the area that I will be neglecting to account for is very small. Whereas if this one, if I have this one big curve and I will just simply have one trapezoid here, then I leave these areas unaccounted for. Okay, so this is just a one interval trapezoidal rule. Isa lang, kung sa aton language, isa lang ka-trapezoid ang gimbutang mo under the curve to approximate its area. Now, the formula in deriving the process of deriving rather the formula for the trapezoidal rule uses the process of linear polynomial interpolation. Now, I think everybody knows how to interpolate. So we use linear polynomial interpolation in that case. To sum up or to simplify the thing, when you interpolate, I think in high school they taught you already how to interpolate. You're trying to find the value of something in between two things. So that's interpolation. So we use, it's a linear process actually. So even if you don't place the word linear here, it's understood that when you do interpolation and even extrapolation, it's a linear process. Now, the main focus, I'd like to annotate here. I can't find my annotation. Okay, sorry guys, wait. The main focus of the trapezoidal rule is this particular formula. The integral of the function of x dx is equivalent to h over 2 times f of a plus f of b. F of a and f of b. The value of the function when x is a, the value of the function when x is b. This h is actually the difference between the upper limit and the lower limit of your integral. Because this a and b actually class, the a and b here are the limits of your integral. So this is how you approximate the value. So you replace an integral process by a simple arithmetic. So this is not even algebra. This is a simple arithmetic formula. You just simply add the terms that you have here and multiply the sum with h over 2. And that's it. That's the value already of the particular integral. But that's not the exact value. It is just but an approximation. So I will clear my markings here and we will continue. Sorry. Now, if we make 2, so this would be the 2 trapezoids. So I have one here. So this trapezoid here almost covered this part of the curve here and another trapezoid here. Okay. Now, if that is the case, then my formula will now have something in between. So if you recall our original formula, find it hard to annotate. If you recall the original formula wherein we only have one trapezoid, this appears already, this one and this one. Now, if you have two trapezoid, you added two trapezoids, you added this one. The same multiplier here for the sum of these three terms. Now, you have to notice that this time, your h will be now x2 minus xo. Your h a while ago, when you only have one trapezoid, is x1 minus xo divided by 2. I think maybe some of you even encountered this already in your senior high. So this is for the first trapezoid and this is only for one trapezoid and this is for two trapezoids. And this is your trapezoidal rule formula. Now, how do we write this in a more generic form wherein we only need not limit it only to one trapezoid, two trapezoids. We limit it to n trapezoids, meaning I divide my area under the curve using n trapezoids. So how would it be? So we'll clear the drawings again. And you will have something like this. So I have 3. Now notice that now I have in between the summation of the function x sub I starting from I equal to 1 to n minus 1. I started with the value of the function at x equal to 0 to x sub n. The x equal to 0 class in here, you have to understand, is the lower limit. The x sub n is the upper limit. The application of this formula will be very, very simple when you see the actual example, a problem that is solved. Now, your h then, generically, if it's presented in this particular formula for n trapezoids, will be x sub n minus x sub 0 over n. This is your, shall I say, a generic formula for n number of trapezoids. The trapezoidal rule does not put a limit or a restriction on the number of, shall I say, trapezoids that you will use. You can use even number of trapezoids. You can use odd number of trapezoids. Now, to illustrate the use of that formula, we have here a sample problem which will determine the area under the curve sine of x on the interval 0 to pi. You may be wondering, why Miss approximate the value of this particular integral wherein this one is elementary? Because I know you know how to integrate this. This is just but for illustration purposes. This is for illustration purposes on how the formula works, the trapezoidal rule formula works. In actual practice, the function that is given here most of the time is non-elementary. The functions that were given to you at the start of the slide. So take for example, you are asked to determine the value of the area under this curve wherein you use 6 trapezoids and then 12 trapezoids. So 6 subintervals or 12 subintervals. So if we will use first, or we will try to find the value of the area of that particular curve using 6 trapezoids or 6 divisions, your A will be 0, as I have mentioned. Your B will be the pi, your upper limit, and your f of x, of course, is the sine of x. That's your function. Now, your n is 6, so we determine the value of the h using the formula b minus a over n. So your b is pi minus a, which is 0, divided by 6. This tells you that the height of your trapezoid will be incremented or increasing by a factor of pi over 6. What do you mean by that, Miss Ali? So meaning, the first x that you will use for the first division will be 0. So you will have 0x. Why 0x? Because you started with 0. So this is 0. Then you increment the x using the pi over 6. So this is pi over 6 for the first division. You add another pi over 6, that would be 2 pi over 6. You add another pi over 6, that would be 3 pi over 6, until you reach the upper limit, which is pi. And then this is pi also. The 6 pi over 6 is also pi. Okay, you get it? So you start with the lower limit, you end with the upper limit, incrementing it using this one, the h, the pi over 6. Then what you do, you already have 1, 2, 3, 4, 5, 6, 7. You have 7 values of x that you will substitute to the function of x. So you start with sine of 0, sine of pi over 6, meaning you substitute the x's here that you have. And this will be the corresponding value of the function. What will you do with it? You substitute it to the formula for the trapezoidal rule. What's the formula? It's h over 2. That's our formula. So pi over 6 divided by 2. Then you just copy the values that you have here. So f of 0 is sine of 0. The f of 1 is sine of pi over 6. You have to multiply it by 2. Notice that in the middle, all the functions are multiplied by 2. So it's only the beginning, the lower limit, and the end, the upper limit, that does not have a multiplier of 2. the functions in between are multiplied by 2. So what you do, you get the sum of these 7 terms and multiply it with each over 2. Your answer will be somewhere like this. Now, having an error of 2.2951 on the actual. So meaning, if you're going to use your calculator and finding the sign of x from 0 to pi, your answer will be different than this one. But what would be the difference? It's very small. That would simply be 2.29%. This is the best approximation that you can have using trapezoidal rule for now, for this particular problem. Now, what happens if you will increase the division? You make n equal to 12. So we will clear all drawings here and we will proceed with n equal to 12. The same procedure actually. So what you do, your n is equal to 12. You solve for another each. Upper limit minus lower limit over n, which is 12. So your increment now will be, sorry class. So your increment now will be pi over 12. Okay, now what will happen? You still start with 0. You still end with pi, but you will increment using pi over 12. So you will have 13 values of x here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This is the 12, this is the 13. And for those 13 values of x, you will also solve 13 functions of x. And the solution actually to these types of problems is always tabular in the form of table. What you do, the same thing as what we did a while ago. You have already the h, which is pi over 12. You divide it by 2. Then you multiply it to the sum of this. The first function and the last function is not multiplied by 2. The middle functions were multiplied by 2. So you have multiplied the function by 2. Now, look at the error when you increase the number of divisions or intervals. The error is just 0.57%, smaller than the previous one, which is 2 point something percent, which tells us that the greater the number of trapezoids we use as approximation under the area of the curve that we want to determine the area of, the nearer is our answer. It's just like in our language, balaging divide mo siya gagmay-gagmay nga trapezoid, ti ang imo na nga diferensya sa actual is also very small. So that's the purpose of having to increase the number of intervals or division. That way, your answer will be nearer to the actual, or it will become more accurate. Increasing the number of n increases the accuracy of your approximation. Because again, we go back to the fact that this particular process is an approximation procedure only. It approximates, it does not give you the exact answer. Okay, that's your trapezoidal rule. The Simpson's rule differ from the trapezoidal rule just by the use of the formula or in the formula that is being used. It does not use a trapezoid, but it actually uses more or less a curve to approximate another curve. So you have this as the original curve. This is your one-step, one-third Simpson approximation. So it's not a trapezoid anymore, but rather a curve in itself. So the end, you don't end here with a line, but you end with a curve. So that's Simpson's rule. Now, its value, the value of the area is of course expected to be more accurate than the trapezoidal rule based on the, of course, the number of n that we are using. So kung damo ang n, mas mas accurate siya. Now, if trapezoidal rule uses linear polynomial interpolation, this one uses quadratic polynomial interpolation. So interpolating here, but not in the linear manner, but quadratic interpolation. The main focus here is for you to know the formula. So you have the formula here for Simpson's rule. You still have h, which is the difference between the upper limit and the lower limit divided by 2. In trapezoidal rule, this is divided by n. Okay, this one is divided by 2. That each that you have will be divided by 3. Okay? Now, x minus 2, rather, this is, by the way, n. In our case, it's only 2 because we only have 2. Let me go back. So you will see, hindi lang ako mag-erase, so you would, it's still there, my line. It's divided by 2 because of this 2. Okay? Now, it would be divided by n if we have n divisions there. Okay, let me, now. So you have h over 3 and you have the function here at 0. So no multiplier. Here you have a function at the end, the upper limit. And in the middle, class, actually you only see a 4 here. But in the middle, you have an alternate of 4, 2, 4, 2. And it should be ending with 4. Requiring you that your n for Simpson rule should be even. Should be, sorry, even number. Your trapezoidal rule does not have any restriction as to the value of the interval. Your Simpson rule required that n should be even. Okay, so n even division. So this is your formula for Simpson's rule. If you'll have something generic for Simpson's rule, it would be something like this. So this is a 2-step 1/3 Simpson rule. So this time you already have 4. So we did not use 3 because n should be even. So we have 4. In that case, you will have a formula here that is stating what I have mentioned. So you see this? You have an alternate already of 4, 2. So a while ago, you only see a 4. It ends with a 4 here. No multiplier here, no multiplier here. Your formula is delta x over 3. See this? So if you have the area of a particular function approximated using Simpson's rule, this will be your generic formula for that. Delta x over 3, then you have this, requiring you that n should be even. Your sub-intervals or your intervals, your number of division should be an even number. Okay, I have 2 minutes left. I will just borrow probably 3 more minutes of your time. Okay, clear? Now, if we will have an example for this particular Simpson's rule, we have this. The distance covered by a rocket in meters is given by this integral, wherein you will have 8 as the lower limit and 30 as the upper limit, and this is your function. Class, I'm saying this is your function. Sorry. This is the function. It's quite long compared to the one we had in the previous example, which is the sine of x. Now, if we estimate the x value, the distance covered by the rocket in meters, your x here would be equal to, using your Simpson's rule. So this is your h divided by 2 divided by 3. So h divided by 2 divided by 3, that would be b minus a divided by 6, because these two you will multiply. So that gives you a 6 here. You have an f of a plus 4 function of a plus b over 2 plus function of b. This is for the lower limit, and this is for the upper limit. And these are for the functions which will alternate by 4 to ... You should have a 4 ending. Okay? Now, your A is 8, your B is 30. If you add the two, that would be, and get the average, that would be 19. Okay, 19. Now, how do we apply these values that you have here? Okay, I will clear markings here. We'll proceed. So if you have the function, this is the function already, copied class. It was copied from the original integral. This is your function. The f of 8 is your f of equivalent to f of 0. If 0 is your initial or your lower limit. So you just substitute 8 there. The next thing is f of 30. Why f of 30? Why find the f of 30? It's because your interval here would be, let me go back. I cannot go back. Yes. 30, it's 30 that you have there, right? Now, a plus b divided by 2 is the middle interval, the 19. So the f of 30 is actually the end. So let's say upper limit, do not note that this is your, let's say this is your a and this is your b, and this is the somewhere in between, the middle, the f of 19. Where is the f of 19 coming from? It's the a plus b divided by 2. So you have the b here, 30 minus 8 divided by 6 times the function value at x equal to 8. This one is the lower limit plus the function value at the upper limit times 4 times the function value at 19. Wherein you have a plus b divided by 2. So you incremented this one by 11. Plus 11, that would be 30. So you increment by 11 to get the middle value, which is 19. If you substitute everything, you add the function values here and you multiply it to 22 over 6. This is the corresponding value, 11,065.72. That's your Simpson's rule. Upper limit, lower limit, and somewhere in the middle. So you incremented using 11 as your increment. Now, I will clear here. Let's check what we have there on the next slide. So accuracy of the of finding the approximate area using the two methods will depend on the number of the subintervals chosen. So the greater the number of subintervals, the closer to the exact answer is your value. That's for the two numerical integration approximation procedures. Okay, so let me check my time. So 3:33, I used up 3 minutes of your time. I will stop sharing now. Class, if you have any question, don't hesitate to ask me, even in the GC, or if you're hesitant, you can privately message me as to any questions that you may have on the two methods discussed this afternoon and the finishing part of the improper integral. So next week, Monday, will be your quiz day. We will have our lecture on Wednesday. Okay? So I will end now. Bye for now, but you may ask questions through the GC and the email or even in Canvas. But before you go, I'd like to check the attendance. First, because we are instructed to check attendance. Okay. Bye for now, class. Thank you. Hope to hear from you next week again.
Thank you, Miss.
Thank you.